On September 15th, 2017, a machine 3 billion kilometers from Earth turned its antenna toward home one final time, and then deliberately flew into its own death. NASA didn't lose Cassini. NASA killed it, on purpose. And the reason why is stranger than anything in science fiction. But here's what nobody expected. 8 years after that spacecraft was vaporized in Saturn's atmosphere, its data is still speaking. In late 2025, scientists opened files Cassini recorded 17 years ago, and what they found inside may be the strongest evidence yet that we are not alone. Stay with me, because this story is not over. Imagine spending 20 years of your life building something, 7 years flying it across the solar system, 13 years watching it succeed beyond your wildest dreams, and then being forced to destroy it with your own hands. That is exactly what happened inside NASA's Jet Propulsion Laboratory in September of 2017. Engineers who had devoted entire careers to a single spacecraft gathered in a control room in California and watched the screens as their creation transmitted its final heartbeat. Some of them wept openly, and when the signal finally flatlined at 4:55 in the morning Pacific time, the room went silent. But to understand why this moment mattered, why it still matters today more than ever, we have to go back to the beginning. Because Cassini was never just a spacecraft. It was humanity's eyes at the edge of the known. The Cassini-Huygens mission launched in October 1997, a joint project between NASA, the European Space Agency, and the Italian Space Agency. It was one of the largest, heaviest, and most ambitious interplanetary spacecraft ever constructed, roughly the size of a school bus, carrying 12 scientific instruments and a European-built lander named Huygens strapped to its side. Its destination was Saturn, nearly 1.5 billion kilometers from Earth. But here's the part most people never think about. The journey alone took almost 7 years. 7 years of silence, of gravity assist flybys past Venus, Earth, and Jupiter, of engineers on the ground growing older while their machine coasted through the dark. When Cassini finally slipped into orbit around Saturn on July 1st, 2004, it became the first spacecraft in history to orbit the ringed planet. And almost immediately, it began rewriting the textbooks. Think about what Saturn was before Cassini. A blurry ball with rings, photographed briefly by Voyager flybys in the early 1980s, snapshots taken at high speed, gone in days. Cassini stayed for 13 years. It watched entire seasons change on a world where a single year lasts 29 Earth years. It photographed a hexagonal storm at Saturn's North Pole, a six-sided jet stream larger than planet Earth itself, a geometric shape so perfect and so enormous that scientists are still debating exactly how it holds its form. It watched a monster storm erupt in Saturn's northern hemisphere in 2010 and wrap itself entirely around the planet, a tempest that eventually stretched 300,000 kilometers, long enough to circle Saturn completely and collide with its own tail. And in January 2005, it did something no mission had ever done. It dropped the Huygens probe through the thick orange haze of Titan, Saturn's largest moon, achieving the most distant landing in human history. Huygens descended for 2.5 hours and revealed a world with rivers, lakes, and rain. Except the liquid wasn't water. It was methane, an entire alien hydrological cycle running on natural gas at minus 179 degrees Celsius. But all of that, the storms, the hexagon, the landing on Titan, turned out to be the opening act. Because in 2005, Cassini noticed something strange about a small, bright, frozen moon that almost nobody had been paying attention to. A moon called Enceladus. It's tiny, only about 500 kilometers across, small enough to fit inside the borders of many countries. It should have been a dead ball of ice, geologically silent, frozen solid for billions of years. And yet Cassini's instruments detected something impossible. The moon was breathing. Enormous geyser-like jets of water vapor and ice were erupting from cracks near its south pole, blasting material hundreds of kilometers into space. Read that again. A frozen moon, 10 times farther from the sun than Earth, was actively venting water into the void. And this is where everything changed. Over the following years, Cassini flew through those plumes again and again, tasting them with its instruments. The evidence assembled piece by piece like a case file being built by a patient investigator. The jets contained salt, which meant the water had been in contact with rock. The moon wobbled slightly in its orbit, and the precise pattern of that wobble revealed that its icy outer shell was not attached to its core, which could only mean one thing: a global ocean of liquid water wrapped around the entire moon, hidden beneath roughly 20 to 25 kilometers of ice. Then came the discovery of silica nanoparticles and molecular hydrogen in the plumes, chemical fingerprints, suggesting hydrothermal vents on the ocean floor, places where hot, mineral-rich water rises from the rock below. On Earth, hydrothermal vents are crowded with life. Some scientists believe they are where life on our planet began. And here was Cassini telling us that the same machinery might be running right now in the dark under the ice of a moon of Saturn. Now hold that thought, because it's the key to everything that comes next, including the reason Cassini had to die. By 2017, the spacecraft was running out of fuel, not electricity. Its plutonium power source could have kept the instruments alive for years. Fuel, the propellant needed to steer, to adjust its orbit to point its antenna at Earth. And a spacecraft that cannot steer becomes something very dangerous. A derelict, drifting unpredictably through a system of moons. Here's the problem NASA faced, and it's a problem almost nobody in the public ever heard about. Cassini was not sterile. It left Earth carrying microbes, hardy bacterial spores that, according to everything we've learned about extremophiles, might survive decades in the vacuum of space. If a dead, uncontrollable Cassini ever crashed into Enceladus or into Titan, it could contaminate a potentially habitable alien ocean with Earth life. Imagine the catastrophe. Imagine a future mission discovering life on Enceladus and never being able to prove it wasn't something we put there ourselves. The greatest discovery in human history, poisoned by our own fingerprints. So, NASA made a decision that sounds like a paradox. To protect the possibility of alien life, they would destroy their own spacecraft. They called it the Grand Finale, and it was not a quiet retirement. It was the most daring flying Cassini ever did. Beginning in April 2017, engineers used one last gravitational kick from Titan to hurl the spacecraft into a trajectory no mission had ever attempted. 22 dives through the narrow gap between Saturn's cloud tops and the innermost edge of its rings. A corridor roughly 2,000 kilometers wide, threaded at speeds of over 100,000 kilometers per hour, 22 times. Any collision with even a grain of ring debris at that velocity would have been fatal. Mission planners genuinely did not know if the spacecraft would survive the first pass. It survived all of them. And in doing so, it measured the mass of Saturn's rings from the inside, sampled the planet's upper atmosphere directly, and mapped its gravity and magnetic field with a precision that shocked scientists, revealing, among other things, that Saturn's rings are likely far younger than the planet itself, possibly only tens to hundreds of millions of years old, which raises a question that still has no confirmed answer. If the rings are young, what created them? Did Saturn destroy a moon? Did it capture and shred a passing comet? Dinosaurs may have walked the Earth before Saturn had its rings. Sit with that for a moment. Then came the final day. On September 14th, 2017, Cassini turned its cameras toward the Saturn system one last time and took its farewell portraits. It photographed Titan, the moon where it had landed a probe. It photographed Enceladus, and in a moment of almost unbearable poetry, its final image of that little ocean moon caught it setting behind Saturn's edge like a sunset. It photographed the rings it had spent 13 years studying, and its very last image looked toward the dark side of Saturn, at the exact patch of atmosphere where hours later the spacecraft itself would burn. Cassini photographed its own grave. Then it turned its antenna toward Earth, locked on, and never looked away again. From that point forward, it had one job: transmit everything until the very end. In the early hours of September 15th, Cassini plunged toward Saturn at more than 120,000 kilometers per hour. As it hit the upper atmosphere, its small thrusters fired desperately, fighting to keep the antenna pointed at Earth against the thickening air. For about 90 seconds, the machine fought physics itself, sampling Saturn's atmosphere directly and streaming the data home in real time, doing science literally until its final breath. Then, the atmosphere won. The spacecraft began to tumble, the signal broke on the Thinamino, and within minutes, Cassini heated, melted, and disintegrated, becoming, in the end, part of the planet it had studied. It is still there. Its atoms are part of Saturn now. But here's the detail that gives people chills. Because Saturn is so far away, Cassini's final radio signal took 83 minutes to cross the void to Earth. When engineers in California received the last transmission and watched the line go flat, the spacecraft had already been dead for almost an hour and a half. They were listening to the voice of a ghost. And that, most people assume, is where the story ends. A beautiful mission, a noble sacrifice, a chapter closed. But that assumption is completely wrong. Because Cassini sent home 453 gigabytes of scientific data and over 450,000 images. A mountain of information so vast that scientists knew, even in 2017, that it would take decades to fully understand. The spacecraft was gone. The data was not. And buried inside that data, sitting quietly in archives for 17 years, was a message that would only be decoded in 2025. Let me take you back to a single moment. October 9th, 2008. On that day, Cassini performed a flyby of Enceladus, codenamed E5, and it was unusual. The spacecraft tore through the moon's icy plume at nearly 18 kilometers per second, significantly faster than other flybys, passing within about 21 kilometers of the surface. Fresh ice grains, ejected from the moon's interior just minutes earlier, slammed into the spacecraft's cosmic dust analyzer. At the time, the data from that flyby was messy, overwhelming, almost impossible to interpret. Researchers published early analysis in 2011, noting organic molecules were present but unable to determine what they actually were. So the mystery sat there for years. While Cassini flew on, while it died, while the world moved on, those readings waited in the archive like a sealed envelope. And then, in October 2025, the envelope was finally opened. A team led by planetary scientist Nazaire Khawaja published their findings in the journal Nature Astronomy and revealed new complex organic molecules in those fresh ice grains from Enceladus, a clear sign that complex chemical reactions are taking place inside the moon's hidden ocean. Here's why the speed of that old flyby turned out to be the secret. At lower impact speeds, shattering ice creates clusters of water molecules that hide the signals of organic compounds. But when grains hit the detector fast, the water signal breaks apart, exposing molecules that had been invisible in every other measurement. In other words, the violence of that 2008 flyby accidentally created perfect laboratory conditions. Cassini had captured the evidence all along. It just took humanity 17 years to learn how to read it. So what exactly did they find? The team identified molecules never before seen in the Saturn system: aliphatic esters and alkenes, heterocyclic compounds, ethers, and nitrogen and oxygen-bearing organics. If those names mean nothing to you, here's the translation that matters. Esters and ethers can be components of lipids, and lipids are fundamental to life as we know it. These are the kinds of molecules that sit on the chemical pathways leading toward biology. And critically, these grains were pristine. Previous organic detections came from ice grains in Saturn's E-ring that were potentially years or even centuries old, weathered and altered by intense space radiation. But these compounds were just minutes old, in ice fresh from the ocean below the surface. As co-author Frank Postberg put it, this proves the complex organics Cassini detected are not artifacts of long exposure to space. They are readily available inside Enceladus' ocean right now. This is not chaos in the data. This is chemistry with direction. But here's where it gets even more interesting. That October announcement was not an isolated result. Late 2025 became a cascade of Cassini revelations, one after another, as if the dead spacecraft had decided to start talking again. In November 2025, analysis of Cassini data revealed surprising heat flow at Enceladus' north pole, showing the moon is releasing energy from both poles, not just the south, a balance of heat that could allow its subsurface ocean to remain stable over long timescales. Why does that matter so much? Because habitability isn't just about ingredients, it's about time. Life needs an ocean that persists for millions, maybe billions of years. A moon leaking heat in a stable, balanced way is a moon whose ocean isn't a temporary accident. It's a long-term environment. That same month, supercomputer simulations built on Cassini's measurements showed that the plumes are losing 20 to 40% less mass than earlier estimates suggested. Refining our picture of what's happening beneath the ice and sharpening the models future missions will depend on. And by December 2025, scientists summarizing the state of the evidence could say something remarkable. Analysis of fresh plume material confirms organic molecules, abundant hydrogen, and nearly all the key elements life requires, supporting a global subsurface ocean with active hydrothermal systems. Think about what that means. A world 1/25th the size of Earth, and it has checked almost every box on the habitability list. Now, step back and look at the full picture, because this is what mainstream headlines keep missing. Enceladus is not just a place that might have life. It is arguably the most accessible, potentially habitable environment in the entire solar system. Europa, Jupiter's ocean moon, hides its water under an ice shell that may be far thicker, locked inside one of the most lethal radiation environments known. Mars may have had life billions of years ago, past tense. But Enceladus is doing something no other world does. It is actively throwing samples of its ocean into open space every second of every day, free of charge. You don't need to drill. You don't need to land. You can fly through this plume and collect the ocean directly, which is exactly what Cassini did, without even being designed for it. Cassini launched nearly 30 years ago, back when Enceladus' ocean and plumes weren't even known to exist. Its instruments were never built for astrobiology, and yet they came within reach of the biggest question ever asked. So ask yourself, what would a spacecraft find if it went there on purpose, carrying instruments designed specifically to detect life? We may find out, because these discoveries have set something in motion. The European Space Agency has begun studies for an ambitious, dedicated mission to Enceladus, a spacecraft that would fly through the jets and even land on the moon's south polar terrain to collect samples. ESA announced in 2024 that Enceladus is one of its top targets, with the lander expected to sample the south polar region directly. And every one of these new results from Cassini's archive is now shaping which instruments that future spacecraft will carry. Meanwhile, NASA's Europa Clipper is already en route to Jupiter to study Europa, another leading candidate in the search for life beyond Earth. A machine that died in 2017 is writing the blueprints for missions that won't arrive until the 2040s. That is not a legacy, that is a relay race. And Cassini is still holding the baton. And here is perhaps the most staggering fact of all, the one that reframes this entire story. Much of the data from Cassini's cosmic dust analyzer still hasn't been analyzed. Let that sink in. The discoveries of 2025, the esters, the ethers, the hidden heat, the refined plumes, all of it came from a fraction of what's sitting in the archive. Somewhere in those unexamined files, recorded by a spacecraft that no longer exists, there may be signals no human being has ever looked at. The scientists working on this describe it as phenomenal. The mission keeps teaching, keeps surprising, keeps producing front-page science nearly a decade after its destruction. In a very real sense, Cassini is not finished. It's just slower now. It speaks through archives instead of antennas. There's also a quieter, more human dimension to this story, one worth pausing on. The researchers who cracked the EFA's flyby data spent years running laboratory experiments, firing ice grains at detectors, learning how impact speeds distort chemical signatures, building the decoder ring, one painstaking test at a time. One outside scientist praised the team for the sheer diligence and patience required to finally understand what the instrument had recorded. This is what discovery actually looks like, not a eureka moment, a 17-year translation project. And it forces an uncomfortable question about every space mission we've ever flown. How many other answers are already in our possession, sitting in old data from Voyager, from Galileo, from missions long dead, waiting for someone with new tools and enough stubbornness to find them? The universe may have already told us things we simply haven't learned to hear. None of this means life has been found. Let's be precise, because precision is what separates real science from hype. What Cassini's data shows is habitability, liquid water, chemical energy, essential elements, and complex organic chemistry operating together in one environment. Those are the conditions for life, not proof of it. The molecules discovered could be produced entirely without biology. That's exactly why a return mission matters so much. And as the lead researcher himself pointed out, even finding no life on Enceladus would be a huge discovery, because it would raise profound questions about why life is absent in a place where all the right conditions exist. Read that again. Either answer changes everything. If life is there, we learn that biology emerges wherever water meets rock and energy, which would mean the galaxy is likely teeming with it. If life is not there, we learn that habitability is not enough, that something rarer, something we don't yet understand, had to happen on Earth. Both outcomes rewrite our place in the universe. There is no boring result. So let's return one last time to that control room in September 2017, to the engineers watching a flat green line morning a machine. They thought they were witnessing an ending. They weren't. They were witnessing a handoff. Cassini's final act was not the plunge into Saturn. It was the archive it left behind, a time capsule that keeps detonating with new knowledge year after year. The spacecraft was destroyed specifically to protect Enceladus, and now from beyond its own grave, it keeps building the case that Enceladus was worth protecting. There's a strange symmetry in that. We killed our explorer to keep an alien ocean pure, and the explorer's last testament is telling us to go back. Which leaves us standing at the edge of the biggest question our species has ever asked, closer to an answer than we have ever been. Beneath 20 kilometers of ice, on a moon smaller than most countries, warm water is rising from hydrothermal vents in total darkness, carrying complex organic molecules toward the surface, where geysers launch them into space like messages in bottles. Cassini caught some of those bottles. In 2025, we finally opened them, and inside, we found the chemistry of possibility. But the ocean is still down there. Still warm, still churning, still unread. Is something swimming in that darkness right now, 3 billion kilometers away, utterly unaware that a small blue world has noticed it? Or is Enceladus a perfect, empty laboratory, all the ingredients of life and no spark? A dead spacecraft has carried us this far. The next answer will require the living to go and get it. And when that mission finally flies through those icy jets with instruments built to detect biology itself, what happens to us? To our religions, our philosophies, our idea of what we are on the morning the results come back? Because one way or another, they will come back. The only question is whether humanity is ready for what they say.